28 minutes for the Q&A session. So I'd like to prioritize members of the audience if they would like to retype or recopy their question into chat, give you the opportunity to ask your question or re-ask your question. We have 150 people here, but if folks want to raise their hand, we can also invite you to unmute and ask your question directly.
Maybe I can start maybe with a
Please
question.
Please do, Caspar. Thank you.
I hope it's okay to ask a question of a very practical nature. Tanya, thanks a lot for your presentation. Very impressive. I was wondering what kind of materials have you used for your eversion robots, in particular the ones that are crunched up and then are unfolding from the basket that sits at the tip?
Yeah, thanks for the question. Yeah, for those ones in particular, we were actually using Dyneema was the material. And so for the ones that we were scrunching, but we've been moving more and more towards just using things like TPU. It seems to work quite well in general for scaling them down. We used to use more synthetic like fabrics on nylon and other things, but it's quite hard to make them reliably at the small scale we found. And the thickness really makes a big difference. So the thinner the material, the scaling laws work much better for growth as well.
Yep, that's also our experience yeah, the thinner the better. Yeah, thanks a lot.
Along those lines, I have a question for both Tanya and Caspar about everting robots. Obviously, a huge structural challenge here. Is there any work in either of your labs or that you know of in terms of local closed loop control? So a sensor that's everted at the tip and somehow modulates bending direction. How do you go about trying to close the loop on control in these kinds of systems?
Okay, shall I start? Yes, we have done some work. So the earlier work was camera based, and I mean we were cheating a bit because we were observing the robot in free space, so maybe not wouldn't work inside the colon. But for example, in applications like the radioactive environments, remote larger areas where you want to scan an area, that could be applicable. And so there we have used the camera to close the loop. So effectively observing the position of the eversion robot and use that to then control the pressure appropriately that we are using to move the robot forward. But also we were looking at the pressure that you would need to make it bend. So we have used mainly integrated pouches that can be inflated and allow us then to achieve a lateral movement.
Tanya, any thoughts?
Yeah, no, I think this is a great question. I think we mentioned the challenge with integrating sensors into these types of systems, but we've done some work with actually integrating a permanent magnet at the tip of the robot and then using external sensors to sense the location of the magnet. And through that, localizing the tip, the magnet will stay at the tip the entire time if you use this ring magnet, and then using that to close the loop for control.
Very, very cool. Thank you very much. So I see in my chat queue here, Nick Wilkinson has a question for Thrish. Nick, if you're able, do you want to unmute yourself and just ask your question verbally?
Thank you. Yeah, let me just. Thrish, thank you. That was an awesome talk, and I love this idea of ghost circuits. And now I want to work with them. So I'm wondering, are there like general features of ghost circuits? Might there be principles for ghost circuit design?
Yeah.
That kind of.
Yeah. So the important thing is the building blocks of ghost circuits are dynamic systems on their own. So when one part of the other, they exhibit some behavior, they emerge, and then the reaction gives another reaction. So that all these interactions emerge and then settle down in a very synchronized kind of a bigger circuit. So that is why I call it a ghost. Is like it is not to be seen at the beginning. So it is seen at the end of the dynamic process. So it emerges, and then certain conditions are required for it to emerge. And then if the conditions are not there, they just dissolve. So basically, you can shut down the conditions by stiffening the body, for example. So you just turn it off, right? So, and then the circuit disappears. So let's say if the fish is alive, it can actually piggyback on that passive dynamic circuit by actively swimming too, but it is just topping up some energy, not really entirely taking over. So the capsule, for example, it can be activated, it can be motorized, but it is not going to destroy that whole energy harvesting process from the peristaltic waves. So basically, we have to design the morphology of the thing we design, which is, let's say, the capsule, to harness energy from the peristaltic waves as much as possible, and then on top of that, actuate. So without completely taking over the natural dynamics. So then we have to think about system of systems approaches to design.
Thank you.
Great, thank you. Returning to the topic of everting robots, there's a question in chat from Leona Costi. Do you want to unmute yourself and ask your question, if you're able?
There's no microphone at their side.
Okay, I will ask your question for you. You were wondering if there is an alternative to pneumatics in these systems. At the Space Agency, we would like to use them for moon's lava caves, but pneumatic on the moon is prohibitive. How do we tackle this problem?
Yes, yes. We also, for some medical applications, same thing. You don't want to use pneumatics. So for our endovascular robots, for example, we've used water, saline for the working fluid. And I think that, yeah, Bill had a question earlier as well about other types of working fluids. And so I mentioned that there's other groups. Christos Bergelis' group also has used a low melting point alloy for the growth, which then allows you to also stiffen the robot as well. So I think, yes, there's different working fluids that can be used besides pneumatics for these various applications.
Just checking, is it because of air, oxygen that is not working on the moon? I'm asking because I'm also in discussions with colleagues interested in creating soft inflatable structures that could be used in space, so in vacuum, to, for example, capture space debris. And they have not, voted against using pneumatics. If it's the oxygen, what about CO2 on the moon? Any leak would be fatal. What do you mean by this? I mean, obviously, if there is a puncture in your structure, the air, would come out. But what do you mean by fatal?
The pressure difference is so great that even if no puncture, it can be really disrupted.
So the robotic structure might be destroyed, or definitely will lose its function. But the pressure difference might, I mean, we can also turn it around, on ground where we have air, atmospheric pressure, we need to actually pressurize our structures more than might be required on the moon or in space. So yeah, I would think there are also options if you use air on the moon or in space.
Okay, thank you. Bill Langton, I know you had a couple questions in chat, but please feel free to re-ask them.
So this was a question for Tanya, and she did answer it sort of privately, but maybe we could discuss it widely. It was an idea that in plants, the plant mostly grows from the tip, and I was wondering if there was some way of using that analogy within the soft robotics with the tubes extending, whether there was some way of supplying material to the tip, which could then become in some way incorporated into the tip and grow further. I think Tanya had some ideas about this being tried in some cases.
Yeah.
No, Casper, go for it.
What comes to my mind is work by Barbara Mazzoli from SSSA in Italy. In a nutshell, they have put a 3D printer at the tip of a robotic structure, and by printing the tip again and again on top of the existing tip, you effectively can achieve growth, which is similar to the way plants are probably doing it to some extent. So that's the kind of work I know about.
But would that be suitable for Tanya's application, where she wants to do this for surgical applications?
Yeah, that's a good question. I think that these types of robots require, at least in a lot of the designs, having something at the tip of the robot that can do the sort of extrusion, for example, or polymerization, depending on the printing method. So I think maybe depends on the scalability of that mechanism, likely. I think that a lot of the applications right now of these types of robots is maybe more for exploration and kind of these larger scale applications. So probably just depends on the scaling being the main question there. Yeah, but I agree. This is a nice way of using this idea of bioinspiration to grow the body as well.
Great, thank you.
Josie, you had a question about medical systems.
Thank you. Yes, I think it was already partly answered, but by I think Casper's previous question. But for all these medical considerations, it was actually, I will answer another question, given that Casper also already asked that one, about how do we validate soft robotic systems for medical considerations? Is it enough that it's soft? How do we have these guarantees of safety, or from a medical or even regulatory perspective? Does it change the perspective that it's soft, that it's compliant, that it's exploiting kind of embodied intelligence, or does this help or does this hinder?
So I would say the relevant bodies don't care whether something is now called soft robot or not. One has to go through the proper certification process. And yeah, one has to satisfy relevant safety requirements. And they are quite stringent, especially if you create systems that are mechatronics or have electronic components in them. So maybe there we have a slight advantage, because most of the systems we are working with are just mechanical structures, and we are pumping air inside, so no electronics, no computer inside the body at least. So from that perspective, maybe a slight advantage. But another aspect, just quickly to mention, everything you want to put inside a human body needs to be biocompatible. So you have to choose your materials in a way that it is not harmful for the human body. Yeah.
I had a question for Eric Diller, actually. Eric, very fascinating materials you're working with. Have you thought about computationally designing the device so there's sort of a more one-to-one mapping between trying to focus the loci of control on a few or one degree or one of the degrees of freedom? There might be a way to simplify the mapping by doing some computational design. Just a thought.
Yeah, some of these are easy to design. A single joint moving, we just want to put the most magnetic material somewhere on that joint. But flexible devices with continuous deformations, it's a really hard design problem. And our intuition about where to put the material and how to magnetize it falls quite short. So there's a lot of opportunity, and those in our field are working on ML powered approach to this problem of optimizing where to put the material and how to orient it, basically. So it's a good problem. A good question. That's the key issue. Yeah.
Great. Thank you. I'm not seeing any other questions arriving in chat. We do have another opportunity later this afternoon to engage all together in discussion about the talks this morning. So perhaps we'll pause here and give everyone a chance to indulge. Casper, I see your hand
Maybe
up.
just a quick one, because I
Sure.
see Leone Costi has responded again. And indeed, you cannot provide extra air on top of what you take with you to this remote location on the moon. But if people travel, then you need air anyway. If you want to use your thrusters moving through space, you also need air, oxygen to to burn your fuel. So it's not something completely new to take now air to these remote areas. And you could also consider recycling the air. So use the air to grow your robots or pneumatically actuate them, and then retract the air again into containers. As long as everything is fairly airtight, you can operate them for some time.
Great. Thank you, Casper. Okay, I think this concludes this session. Before folks log off, just a reminder, please return at 45 minutes after the hour for our next plenary talk. And I'll also just give an opportunity for any of the conference organizers if there's any logistical notes.
Nope, that is perfect. Yep, we'll start again at 45 past. Thank you so much, Josh, and all the speakers.
Thanks, everyone.
Thank you, Josh.